Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Before we begin tonight's journey, feel free to share what time it is and where you're listening from. It's always wonderful to know where these gentle explorations are drifting off to. Tonight, we're venturing to the very edge of everything we know, and perhaps beyond, the edge of the universe. It's a question that has tickled human curiosity since we first looked up at the night sky and wondered what lies beyond those twinkling points of light. Where does it all end? Is there a wall? A fence? A cosmic "do not enter" sign floating in the darkness? The answer, as you might expect, is both simpler and more wonderfully strange than you might imagine. We'll wander through cosmic horizons and expanding space, through time itself stretched thin, and into realms where even the concept of edge begins to lose its meaning. There's no need to follow every detail. Just let these cosmic ideas drift by like gentle clouds. So settle in, close your eyes if you like, and let's take a slow, peaceful journey to the very boundary of existence itself. Stand in your backyard on a clear night and look up. There they are, thousands of stars scattered across the darkness like scattered salt on a black tablecloth. It's one of the most ancient human experiences, this looking up and wondering. And almost immediately, a question forms in your mind, the same one that's been tickling human curiosity for millennia. Where does it all end? It's such a natural question, isn't it? In our everyday world, everything has boundaries. Your garden has a fence. Your neighborhood has streets that lead to other neighborhoods. Your country has borders. Even the earth itself has an edge, if you count the thin boundary where atmosphere meets the emptiness of space. We're surrounded by edges, limits, places where one thing stops and another begins. So when we look up at the night sky, our minds naturally reach for the same framework. Surely, somewhere out there, all those stars must come to an end. There must be some cosmic shoreline where the universe simply stops. Maybe there's a wall, maybe there's nothing, maybe there's something else entirely. But there has to be something, right? Well, here's where the universe starts to play tricks on our everyday intuition. The cosmos, it turns out, doesn't much care about our comfortable notions of boundaries and edges. It operates by rules so different from our daily experience that even asking, "Where does the universe end?" is a bit like asking, "What does purple taste like?" The question itself might need to be unpacked before we can even begin to answer it. Consider this. When you stand at the edge of a forest, you can see where the trees stop and the meadow begins. When you reach the shore of an ocean, you can feel the sand under your feet and the water at your toes. These boundaries exist in space, and you can visit them, touch them, cross them. But what if the universe's edge isn't that kind of boundary at all? What if it's more like the edge of time, or the edge of existence itself? Our brains, wonderful as they are, evolved to navigate a world of medium-sized objects, moving at reasonable speeds. We're built to understand rocks and rivers, trees and clouds, things we can see and touch and walk around. But the universe operates on scales so vast and in ways so strange that our intuition starts to break down. It's a bit like trying to understand the ocean by looking at a single drop of water, or trying to grasp the concept of 1,000,000 by counting to 10. The numbers alone are enough to make your head spin gently. The nearest star to our sun, Proxima Centauri, is about 25 trillion miles away. That's roughly 4¼ light years, which means that the light reaching your eyes from that star left it over 4 years ago. You're not seeing it as it is now, but as it was when you were 4 years younger, and that's just our closest stellar neighbor. The Milky Way galaxy, our cosmic hometown, contains somewhere between 100 billion and 400 billion stars. And beyond our galaxy, there are somewhere around 2 trillion other galaxies, each containing billions or trillions of stars of their own. The observable universe, the part we can actually see, stretches for about 46 billion light-years in every direction. That's the distance light could have traveled since the beginning of the universe, accounting for the expansion of space itself. But here's the thing that makes this question so beautifully complex. Just because we can see that far doesn't mean that's where the universe ends. It just means that's the limit of our ability to observe. It's like being in a room with thick fog, where you can only see a certain distance. The fog doesn't mark the edge of the world, just the edge of your vision. And that's where things start to get interesting, because the universe's edge might not be a place you could visit, even with the most advanced spaceship imaginable. It might not be a boundary in space at all, but a boundary in time, in possibility, in the very fabric of reality itself. It might be less like the edge of a map and more like the edge of a song, the moment when the music fades into silence. So as we begin this gentle journey to the edge of everything, let's carry with us a sense of wonder rather than expectation. The universe, as we'll discover, has its own ideas about boundaries and edges, ideas that are far stranger and more beautiful than anything our everyday experience might suggest. Take a moment, if you will, and let that thought settle comfortably in your mind. We're about to explore not just the edge of space, but the edge of human understanding itself. Imagine you're a goldfish who's just discovered that your bowl might not be the entire world. That's roughly the position we humans find ourselves in when we start thinking seriously about the universe's boundaries. We live inside what astronomers call the observable universe, a kind of cosmic fishbowl beyond which we simply cannot see. But unlike a goldfish bowl, our cosmic boundary isn't made of glass. It's made of something far more subtle, time itself, mixed with the speed of light and the expansion of space. It's an invisible sphere with Earth at the center, not because we're special, but simply because that's where we happen to be looking from. And the edge of this sphere isn't a wall, it's more like a horizon. Think of it this way. When you stand on a hill and look out at the landscape, there's a point where the curve of the Earth prevents you from seeing any farther. That's your horizon. The observable universe has a similar kind of horizon, but instead of being limited by the Earth's curvature, it's limited by the age of the universe and the speed of light. Light, as you may know, travels very fast, but not infinitely fast. It zips along at about 186,000 miles per second, which sounds impressive until you realize how truly vast space is. The light from the sun takes about 8 minutes to reach your eyes. The light from the next nearest star takes over 4 years, and the light from the most distant galaxies we can see has been traveling toward us for over 13 billion years. Now, here's the key insight. The universe is roughly 13.8 billion years old. That means light from the most distant objects has had exactly that long to reach us. No more, no less. So there's a natural boundary to what we can observe, not because space ends there, but because light from anything farther away simply hasn't had enough time to make the journey to our telescopes. This creates our cosmic horizon, the edge of the observable universe. It's currently about 46 billion light-years away in every direction. Wait, you might think, that doesn't make sense. If the universe is only 13.8 billion years old, how can we see things 46 billion light-years away? The answer is wonderfully strange. Space itself has been expanding while that light was traveling toward us. Imagine a person walking toward you while the ground beneath both of you is stretching like taffy. They started their journey 13.8 billion years ago, but by the time their light reaches you, the expansion of space has carried them much farther away. It's not that they moved through space faster than light. which would be impossible. It's that space itself grew, carrying them along for the ride. So what do we actually see when we look to the edge of our observable universe? The answer is both simple and profound. We see the cosmic microwave background, often called the CMB. This is light from the moment, roughly 380,000 years after the Big Bang, when the universe first became transparent. Before that moment, the universe was so hot and dense that light couldn't travel very far without bumping into something. It was like trying to see through fog so thick that it glowed. But as the universe expanded and cooled, it reached a temperature where electrons could finally settle down with atomic nuclei to form the first neutral atoms. Suddenly, light could travel freely through space. The universe went from opaque to transparent in a relatively short time, and that first light has been traveling toward us ever since, stretched and cooled by the expansion of space into the microwave radiation we detect today. This cosmic microwave background is like the universe's earliest baby picture. It shows us the universe as it was when it was just a toddler in cosmic terms, barely a fraction of its current age, and it represents the absolute limit of what we can observe directly. We cannot see beyond it, not because our instruments aren't good enough, but because there's literally nothing to see. Light from before that time is trapped, unable to reach us through the opaque fog of the early universe. In a way, it's like looking at the surface of the sun. You can see the bright photosphere, the sun's visible surface, but you can't see directly into the interior, not because it's not there, but because the light can't escape. The cosmic microwave background is the visible surface of the early universe, beyond which our view is blocked, not by matter, but by the fundamental opacity of space itself. But here's what's truly remarkable. This boundary, this cosmic horizon, is not fixed. It's constantly growing. Every second, light from slightly more distant regions has had time to reach us. Our observable universe is expanding, not because space is growing, though it is, but because we're seeing light that left increasingly distant sources in the past. It's like standing in a growing circle of lamplight in a dark room, with the circle expanding as more lamps switch on in the distance. And yet, paradoxically, there are parts of the universe that are moving away from us so fast due to the expansion of space that their light will never reach us. Even as our observable universe grows, there are regions that are forever beyond our cosmic horizon. They exist, presumably filled with galaxies and stars and perhaps even life, but they might as well be in a completely separate universe for all the interaction we can ever have with them. This is our cosmic fishbowl, vast beyond imagination, filled with wonders beyond counting, and yet still just a tiny fraction of what might exist. We are explorers limited not by our courage or curiosity, but by the fundamental structure of space and time itself. And perhaps there's something peaceful in that limitation, a gentle reminder that even our grandest questions have boundaries, beyond which lies not emptiness, but simply the quiet mystery of the unknowable. Here's something that might make your head spin gently. Space isn't just empty, it's growing, not growing into something, which would imply there's something for it to grow into, but just growing, expanding, getting bigger in a way that defies our everyday experience, and yet shapes everything we see when we look up at the night sky. Imagine you're holding a balloon with tiny dots drawn all over its surface. As you inflate the balloon, something curious happens. Every dot moves away from every other dot, and the farther apart they were to begin with, the faster they seem to separate. The dots themselves aren't moving across the balloon's surface. They're just getting carried along as the surface itself expands. This is remarkably similar to what's happening with galaxies in our universe, except instead of a balloon's surface, it's the three-dimensional fabric of space itself that's doing the expanding. This idea is both profound and oddly difficult to grasp because our brains aren't wired for it. In our daily lives, when something expands, it pushes into the space around it. A rising loaf of bread expands into the oven. A growing plant pushes into the air around it. But space can't expand into anything because there isn't an anything for it to expand into. Space is all there is, and it's making more of itself as it goes along. The discovery of this cosmic expansion was one of the most revolutionary insights in human history, and like many great discoveries, it came as something of a surprise. In the 1920s, an astronomer named Edwin Hubble was studying distant galaxies, measuring their light to determine how fast they were moving. What he found was both elegant and shocking. Nearly every galaxy in the universe is moving away from us, and the farther away a galaxy is, the faster it's receding. At first glance, this might seem to suggest that we're at the center of the universe, that everything is fleeing from us like we're some kind of cosmic pariah. But that's not what's happening at all. From any galaxy's perspective, it would appear that all other galaxies are moving away from it. It's the expansion of space itself that creates this effect, like our balloon analogy, but in 3 dimensions instead of 2. This expansion has a wonderfully strange consequence. It means that distant objects can appear to be moving away from us faster than the speed of light, without actually breaking Einstein's rule that nothing can move through space faster than light. How is this possible? Because they're not moving through space at all, they're being carried by space as it expands. It's like standing on a moving walkway at the airport. If the walkway could somehow accelerate to incredible speeds. The speed of this cosmic expansion is described by something called the Hubble constant, which tells us how fast space is growing. Currently, it's expanding at about 70 kilometers per second per megaparsec. Don't worry about the units if they make your head hurt. Just think of it this way. For every 3.3 million light-years of distance, space is growing fast enough to carry objects apart at 70 kilometers per second. It sounds fast, and it is. But space is so vast that locally, the effects are almost negligible. In fact, the expansion only really becomes noticeable over truly cosmic distances. Our solar system isn't expanding, the Earth isn't getting bigger, and the distance between you and your coffee cup isn't increasing. Gravity and other forces easily overcome the expansion on small scales. It's only when we look at the spaces between galaxy clusters that we see the expansion in action, gently stretching the cosmic web like taffy being pulled in all directions at once. But here's where it gets even more interesting. This expansion isn't constant. It's actually speeding up, driven by something mysterious that astronomers call dark energy. About 5.5 billion years ago, the expansion of the universe began to accelerate, as if someone had pressed the cosmic gas pedal. We don't know what dark energy is exactly, only that it seems to be pushing space apart with ever-increasing vigor. This acceleration has profound implications for the future of the universe and for what we can observe. If the expansion continues to accelerate, then over deep time, the cosmic horizon will actually begin to shrink. Galaxies that we can see today will eventually disappear beyond our observable boundary. Their light red shifted into invisibility. Billions of years in the future, observers in our galaxy might look out and see a much emptier universe, with most other galaxies having receded beyond detection. The expansion of space also affects our understanding of cosmic boundaries in subtle ways. Because space itself is growing, the edge of the observable universe isn't a fixed distance away. It's constantly changing. Light that left distant galaxies billions of years ago has been traveling through expanding space all this time, getting stretched and reddened along the way. The galaxies that emitted that light are now much farther away than they were when the light began its journey, And then there's the question of what the expansion means for regions beyond our observable universe. If space is expanding everywhere, then presumably there are vast realms beyond our cosmic horizon that are expanding too, carrying with them galaxies and stars and planets that we'll never see. The expansion doesn't stop at the edge of our vision. It continues outward, creating new space, new distance, new isolation. In a way, the expansion of space is both humbling and liberating. Humbling because it reminds us that we're passengers on a cosmic journey we didn't choose and can't control. Liberating because it suggests that the universe is far grander and stranger than we ever imagined. Space isn't just a container for things. It's an active participant in the cosmic story, growing and evolving, and carrying us all along for the ride. So when we think about the edge of the universe, we have to account for this expansion. It's not just a question of where things end, but how the very fabric of reality is changing, even as we try to map it. The universe's boundary, if it exists, might be expanding too, racing away from us at speeds we can barely comprehend. And perhaps that's part of the beauty of it all. Even our most fundamental questions are caught up in this cosmic dance, stretching and evolving along with space itself. You know how the horizon seems to follow you wherever you go on Earth. Walk toward it, drive toward it, even fly toward it, and it simply moves away, always maintaining that same distance where the sky meets the sea or the land meets the sky. The cosmic horizon works in a remarkably similar way, except it's far stranger and more wonderful than anything we experience in our daily lives. When we talk about the edge of the universe, we're really talking about horizons, boundaries beyond which we cannot see or travel, not because there's nothing there, but because the fundamental structure of space and time prevents us from accessing what lies beyond. It's like being in a cosmic fog, where the fog itself is made of distance and time rather than water droplets. The most important of these horizons is what astronomers call the particle horizon, which marks the boundary of our observable universe. This is the distance that light has been able to travel since the universe began, accounting for the expansion of space. Currently, it sits at about 46 billion light-years away in every direction, creating a sphere of observability with us at the center. But here's the thing that makes this horizon so beautifully strange. You can never actually reach it. If you somehow built a spaceship capable of traveling at the speed of light, and you pointed it toward the edge of the observable universe and began your journey, the horizon would race away from you faster than you could pursue it. This isn't because of some cosmic speed limit on spaceships, though there is one, but because the expansion of space itself is carrying the horizon away. It's a bit like trying to swim upstream in a river that's flowing faster than you can swim. No matter how hard you stroke, you're always moving backward relative to your destination. Except in this case, the river is space itself, and it's not just flowing, it's creating new riverbed as it goes along. Even more peculiar is something called the event horizon, which represents the boundary of space from which light emitted today could ever reach us in the future. Due to the accelerating expansion driven by dark energy, this event horizon is actually closer than the particle horizon, sitting at about 16 billion light-years away. This means there are galaxies we can see today whose future light will never reach us. We can observe their past, but not their future. Think about that for a moment. There are stars out there, shining right now, whose light is traveling toward us but will never arrive. The expansion of space will stretch their light so much that it fades into undetectability long before it reaches our telescopes. In a sense, we're watching the universe slowly disappear, one galaxy at a time, as they cross our cosmic event horizon and fade into isolation. This creates a strange temporal asymmetry in our cosmic view. We can see the past of very distant objects, the light they emitted billions of years ago when the universe was young. But we cannot see their present, and we never will. They exist in a kind of cosmic parallel now, separated from us not by space alone but by the expansion of space itself. There's also something called the Hubble horizon, which marks the distance at which objects are receding from us at the speed of light due to cosmic expansion. This creates yet another kind of boundary, though it's more permeable than the others. Objects can cross the Hubble horizon in both directions as the expansion rate changes over time. All of these horizons share a common characteristic. They're not walls or barriers in any physical sense. They're more like boundaries of possibility, limits on what can interact with what across the vastness of space and time. If you could somehow teleport instantaneously to the edge of the observable universe, you wouldn't find a cosmic "Welcome to the universe" sign or a fence marking the boundary. You'd just find more space, more galaxies, more stars, stretching away into distances that were previously beyond your horizon, but which would now be within your new, relocated sphere of observation. This is perhaps the most mind-bending aspect of cosmic horizons. They're observer-dependent. The universe looks different depending on where you're looking from. An alien civilization in a galaxy near our current cosmic horizon would have their own observable universe, overlapping with ours, but extending into regions we can never see. They might observe galaxies and cosmic structures that are forever beyond our reach, while missing others that are clearly visible to us. In a way, this makes every point in the universe the center of its own observable cosmos. It's not that we're special or centrally located, it's that the horizon is defined by the observer. This is both humbling and oddly comforting. We're not at the center of everything, but we're at the center of our own cosmic story, our own sphere of possible experience and knowledge. And then there's the question of what lies beyond all these horizons. The honest answer is that we don't know, and perhaps more importantly, we can't know through direct observation. There could be more of the same, an infinite expanse of galaxies and stars and planets, much like the ones we can see. Or there could be something completely different, regions where the laws of physics operate differently, where space and time have different properties, where the very concept of matter and energy takes on forms we can't imagine. Some theorists suggest that beyond our cosmic horizon lies an infinite multiverse, an endless collection of universe-like bubble chambers, each with its own laws and constants and histories. Others propose that the universe is finite but boundaryless, curved in ways that make it impossible to reach an edge, even if you traveled forever. Still others wonder if the question itself is meaningless, like asking what's north of the North Pole. But perhaps the most beautiful thing about these cosmic horizons is that they remind us of the fundamental mystery that surrounds us. We exist in a pocket of knowability, a small sphere of light and information in an ocean of cosmic mystery. And rather than being limiting, this boundary creates a sense of wonder, a gentle reminder that for all our knowledge and technology and curiosity, we remain explorers on the shores of an infinite unknown. The Big Bang wasn't really big, and it definitely wasn't a bang. It's one of those scientific terms that's both perfectly descriptive and completely misleading, like black hole for something that's not actually a hole, or dark matter for something we can't see, but definitely isn't dark in any meaningful sense. The Big Bang was the beginning of everything we can observe. But it wasn't an explosion in space so much as an explosion of space itself. Picture the most common misconception first: a cosmic bomb going off in empty space, sending matter and energy racing outward into a pre-existing void. That's not what happened. There was no empty space for things to explode into because there was no space at all, at least not in any sense we can understand. The Big Bang was the moment when space and time themselves came into being, along with all the matter and energy that would eventually become stars and galaxies, and much later, afternoon tea and comfortable sofas. It's more accurate to think of the Big Bang as the moment when space began expanding everywhere at once. Not expanding into something, but just expanding, creating more space as it went along. Imagine if every point in the universe suddenly started moving away from every other point, not because they were being pushed apart, but because the very notion of distance was increasing moment by moment. In the earliest moments after the Big Bang, the universe was unimaginably hot and dense. Not hot and dense in one particular location, but hot and dense everywhere, at every point in space. There was no center to this cosmic furnace, no edge where the heat faded into coolness. The entire universe, however large or small it might have been, was filled with the same intense conditions. During the first tiny fraction of a second, something extraordinary happened that cosmologists call inflation. Space itself expanded exponentially, doubling in size many times over in an almost inconceivably short period. This wasn't objects moving apart through space, but space itself growing so rapidly that regions that had been in close contact suddenly found themselves separated by vast distances. This period of inflation helps explain why the universe looks so remarkably uniform in all directions. The cosmic microwave background radiation, that afterglow of the Big Bang we discussed earlier, has almost exactly the same temperature, no matter which way we point our telescopes. This seems puzzling at first, because regions of space on opposite sides of the observable universe have never been in contact with each other, at least not since the early moments of cosmic history. How did they manage to reach the same temperature? The answer is that they were in contact, very briefly, during those first moments before inflation stretched them apart. It's like taking a small, uniformly heated room and then suddenly expanding it to the size of a continent. Every part of that expanded space would still have roughly the same temperature, because it all started out in the same small, well-mixed environment. But here's where the Big Bang becomes even stranger when we think about cosmic boundaries. If the universe is infinite now, then it was probably infinite right from the beginning. The Big Bang didn't create a finite amount of space that then expanded. It created infinite space that then expanded, making the infinite distances between points even more infinite. It's infinity growing into bigger infinity, which sounds like mathematical nonsense but appears to be the most reasonable description of what actually happened. This means that the Big Bang wasn't a localized event that we can point to and say, it happened there. It happened everywhere, at every point in space, simultaneously. There's no cosmic center where the expansion began, no special location that marks the birthplace of the universe. Every point in space has an equal claim to being the center of the Big Bang, because the Big Bang occurred at every point in space. And if the universe is indeed infinite, then the Big Bang involved infinite amounts of matter and energy appearing simultaneously at infinite locations. This isn't just a big explosion, it's an infinitely big explosion, or rather, an infinitely big beginning that doesn't really deserve to be called an explosion at all. Time itself is part of this cosmic origin story. Before the Big Bang, there wasn't a before in any meaningful sense. Time, like space, appears to have begun with the Big Bang. This creates all sorts of philosophical puzzles, like asking what caused the Big Bang if there was no time for causation to operate. It's a bit like asking what's north of the North Pole, a question that seems meaningful until you realize it's based on assumptions that don't actually apply. Some theorists suggest that time itself might be an emergent property, something that arose from more fundamental processes rather than being a basic feature of reality. Others propose that the Big Bang was not the absolute beginning, but rather a phase transition in an eternally existing multiverse. Still others wonder if the question of ultimate origins is simply beyond the reach of scientific inquiry, a gentle reminder that some mysteries might be designed to stay mysterious. But for our purposes, thinking about the edge of the universe, the Big Bang sets important boundaries on what we can know. It represents the earliest moment from which we can receive information, the temporal horizon beyond which our cosmic vision cannot penetrate. Just as we cannot see beyond the cosmic microwave background because the universe was opaque before that time, we cannot see beyond the Big Bang because there was no before for us to see into. This creates a curious situation where the universe's temporal edge, its beginning in time, defines its spatial edge, the boundary of the observable universe. The two are intimately connected, woven together by the expansion of space and the travel of light in ways that make it impossible to separate questions of where does the universe end from questions of when did the universe begin. And perhaps that's the most beautiful aspect of the Big Bang. It reminds us that space and time, matter and energy, are not separate ingredients that were somehow combined to make a universe. They are aspects of a single, unified reality that began together and continue to evolve together. The edge of the universe, if it exists, is not just a boundary in space, but a boundary in the very fabric of existence itself. Every time you look at anything, you're actually looking into the past. It's true when you glance at your hands, though the delay is so brief, just a few billionths of a second, that it might as well be the present. It's true when you look at the moon, which shows you how it appeared about 1 1/3 seconds ago, and it becomes wonderfully dramatic when you look up at the stars, which are showing you their faces from years, centuries, or even millennia in the past. This isn't just a curious fact about light and vision. It's the fundamental limitation that shapes our entire understanding of cosmic boundaries. When we peer out into space with our telescopes, we're not seeing the universe as it is now, but as it was when the light we're observing began its journey toward us. The deeper we look into space, the further back in time we see, until we reach a point where we're observing the universe as it was when it was very young indeed. Light travels at a finite speed, about 186,000 miles per second, which is extraordinarily fast by everyday standards, but leisurely compared to the vast scales of the cosmos. This creates a natural archive of cosmic history written across the sky. The light from the nearest star outside our solar system, Proxima Centauri, left that star over 4 years ago. The light from the center of our galaxy began its journey 26,000 years ago, when humans were still living in small bands and had not yet invented agriculture. But that's just the beginning. The most distant galaxies we can observe are showing us what they looked like over 13 billion years ago, when the universe was less than 1 billion years old and very different from the cosmos we see around us today. These ancient galaxies were smaller, more chaotic, filled with young stars burning bright and fast. The light we see from them today began its journey when the first complex structures in the universe were just starting to form. This creates a peculiar situation when we think about cosmic boundaries. The edge of the observable universe isn't just a spatial boundary, it's a temporal one. We can't see the most distant regions of the universe as they are now, only as they were in the distant past. The galaxies at the edge of our cosmic horizon are undoubtedly very different today than they appear to us, assuming they still exist at all. Some may have merged with other galaxies. Some may have been torn apart by cosmic forces. Some may have evolved in ways we can barely imagine. And here's something that might make you pause gently. Because of the expansion of space, some of the light we observe today left its source when that source was much closer to us than it is now. A galaxy whose light took 10 billion years to reach us might now be 15 or 20 billion light years away, carried outward by the expansion of space during the eons that its light was in transit. This means we're seeing a universe that no longer exists, at least not in the form we observe. It's like looking at an old photograph of a childhood friend, someone who has grown and changed in countless ways since the picture was taken. The light reaching us from distant galaxies is similarly out of date, a cosmic photograph from the deep past. The most ancient light we can observe directly is the cosmic microwave background radiation, that gentle glow from about 380,000 years after the Big Bang, when the universe first became transparent. This light has been traveling toward us for over 13 billion years, carrying information about the cosmos when it was hot, dense, and very different from the cool, spread-out universe we inhabit today. But here's the really remarkable thing. This ancient light surrounds us completely. No matter which direction you point a sensitive radio telescope, you'll detect this faint glow from the early universe. It's like being inside a sphere whose surface is painted with the image of the cosmos as a baby. We can't see beyond this sphere because before that time, the universe was opaque to light. This creates our ultimate observational boundary, not because space ends there, but because information ends there. We can make educated guesses about what the universe was like before it became transparent, and we can infer many things from the patterns we see in the cosmic microwave background. But we cannot directly observe the universe's earliest moments because light couldn't travel freely through the dense, hot plasma that filled space at that time. It's worth pausing to appreciate just how extraordinary this cosmic time machine really is. Every photon of light that enters your eye or hits a telescope mirror has been traveling through space for some amount of time, carrying information about conditions in the cosmos when and where it was emitted. The light from the sun tells us about nuclear fusion happening 8 minutes ago. The light from distant quasars tells us about massive black holes feeding billions of years ago. And because light always travels at the same speed through empty space, we can use it as a cosmic clock, as well as a cosmic messenger. The distance light travels in a year. A light year becomes a unit of both space and time. When we say a galaxy is 10 billion light years away, we're also saying we're seeing it as it was 10 billion years ago. This temporal aspect of cosmic observation has profound implications for our understanding of the universe's edge. The boundary of the observable universe is not just the limit of how far we can see, it's the limit of how far back in time we can see. It's a boundary in space-time, that four-dimensional fabric that weaves together the three dimensions of space with the one dimension of time. And as time passes, this boundary slowly expands. Light from slightly more distant regions has time to reach us, allowing us to see a little further into space and a little further back in time. Our observable universe is constantly growing, though very slowly, as ancient photons complete their multi-billion-year journeys and finally arrive at our telescopes. But there's also a melancholic beauty to this cosmic time machine. Because of the accelerating expansion of the universe, there are galaxies visible to us today whose future light will never reach us. We can see their ancient past, but we're witnessing their final farewell as they recede beyond our cosmic horizon. In a sense, we're watching the universe slowly disappear, one galaxy at a time, as they cross the boundary beyond which no information can ever reach us again. Most of the universe, it turns out, is playing an impressive game of hide and seek. The stars and galaxies that light up our night sky, all the planets and gas clouds and cosmic dust that we can observe directly, represent only about 5% of everything that exists. The remaining 95% consists of two mysterious substances that astronomers have rather uncreatively named dark matter and dark energy, neither of which is actually dark in the way we usually think of darkness. Dark matter isn't dark because it absorbs light. It's dark because it doesn't interact with light at all. It doesn't emit photons. It doesn't absorb them. It doesn't scatter or reflect them. As far as light is concerned, dark matter might as well not exist. And yet we know it's there, in vast quantities, because we can see its gravitational effects on the matter we can observe. Picture a cosmic spiderweb made of invisible silk. That's roughly what dark matter looks like to astronomers. A vast network of invisible scaffolding on which the visible universe hangs. Galaxy clusters sit at the intersections of this web, connected by long filaments of dark matter that stretch across hundreds of millions of light years. The galaxies we can see are like dewdrops clinging to an invisible web, marking the presence of something we cannot directly detect. This invisible scaffolding makes up about 27% of the universe, more than 5 times as much as all the ordinary matter we can observe. Without it, galaxies wouldn't have been able to form in the first place. The gravitational pull of dark matter provided the framework around which gas could condense into the first stars and galaxies. In a very real sense, we owe our existence to this invisible majority. But if dark matter is mysterious, dark energy is downright baffling. It represents about 68% of the universe, making it by far the dominant component of reality. Unlike dark matter, which clumps together and helps build cosmic structures, dark energy seems to be spread smoothly throughout space, pushing everything apart with ever-increasing vigor. Dark energy is what's causing the expansion of the universe to accelerate. About 5.5 billion years ago, the expansion began to speed up, as if someone had pressed the cosmic gas pedal. Before that, the expansion had been slowing down due to the gravitational pull of all the matter in the universe. But dark energy overcame that gravitational brake and began driving the universe apart faster and faster. We don't know what dark energy actually is. It might be a property of space itself, a kind of inherent springiness that becomes more pronounced as space expands. It might be a field that fills the universe, similar to the fields that carry electromagnetic and gravitational forces, but with very different properties. Or it might be something else entirely, perhaps pointing toward physics we haven't discovered yet. What we do know is that dark energy has profound implications for cosmic boundaries and the far future of the universe. If it continues to dominate the expansion, then, over deep time, the accelerating expansion will carry most galaxies beyond our cosmic horizon. Billions of years from now, observers in our galaxy will look out at a much emptier universe, with most other galaxies having receded into invisibility. In the very far future, if dark energy continues to strengthen, it might lead to something called the Big Rip, where the expansion of space becomes so violent that it tears apart galaxies, solar systems, planets, and eventually even atoms themselves. It's a rather dramatic end to cosmic history, though it's still many billions of years in the future, so there's no immediate need to reschedule your weekend plans. The existence of dark matter and dark energy also raises fascinating questions about what lies beyond our observable universe. If the invisible components make up 95% of what we can observe, what might exist in the regions beyond our cosmic horizon? There could be vast structures made primarily of dark matter, invisible cities, and continents that we can never hope to see directly. Some theories suggest that dark matter might interact with itself in ways we don't yet understand, potentially forming complex structures or even alternative forms of chemistry and organization. There might be dark matter planets orbiting dark matter stars, entire ecosystems of invisible matter that parallel our own visible universe but remain forever beyond our direct observation. Dark energy adds another layer of mystery to cosmic boundaries. If it truly is a property of space itself, then it presumably exists everywhere, including in regions far beyond our observable horizon. This means that the accelerating expansion we observe locally is likely happening throughout the entire universe, carrying distant regions apart, at ever-increasing rates. But dark energy might not be constant. It could change over time, potentially even reversing its effects and causing the universe to begin contracting again. Some models suggest that dark energy might oscillate, driving cycles of expansion and contraction over cosmic timescales. If so, the current accelerating expansion might just be one phase in an endless cycle of cosmic breathing. The invisible majority also affects how we think about cosmic connectivity and isolation. In a universe dominated by ordinary matter, distant regions might eventually communicate or interact through some form of super-advanced technology. But in a universe dominated by dark energy, with space expanding at accelerating rates, isolation becomes more and more profound over time. There's something both humbling and wonderfully mysterious about living in a universe where most of reality is invisible to us. It's like being characters in a story where the narrator has decided to keep most of the plot secret. We can see the effects of this hidden reality. We can map its influence and measure its properties, but we cannot directly experience the dark cosmos that makes up the vast majority of existence. And yet there's also something comforting about this cosmic mystery. It reminds us that for all our knowledge and technology, we remain explorers in a universe far stranger and more wonderful than we ever imagined. The darkness that surrounds us isn't empty or threatening. It's full of invisible wonders that shape and support the small, bright corner of reality we call home. Perhaps that's the most beautiful thing about the dark side of everything. It exists, not as an absence, but as a presence we can't quite grasp. It's the universe's way of reminding us that reality is far deeper and more mysterious than appearances suggest, and that the boundaries we can observe are just the beginning of a much grander cosmic story. Empty space, as it happens, is anything but empty. This might sound like a contradiction, but it's one of the most fascinating discoveries of modern physics. The vacuum, that seemingly empty expanse between stars and galaxies, is actually buzzing with invisible activity. It's filled with fields and forces, particles that pop in and out of existence, an energy that fluctuates like a restless ocean, even when nothing else is around. The idea that empty space might not be truly empty goes back to quantum mechanics, that wonderfully strange branch of physics that describes reality on the smallest scales. According to quantum theory, you can never pin down both the position and momentum of a particle with perfect accuracy. But more than that, the theory suggests that energy itself is subject to similar uncertainty. Even in the emptiest region of space, energy levels can fluctuate randomly, creating tiny ripples in the fabric of reality. These fluctuations are so brief and small that they don't violate conservation of energy. They just borrow energy from the future and pay it back almost immediately, like cosmic microloans with incredibly short repayment periods. But during those fleeting moments, virtual particles can pop into existence, exist for the briefest instant, and then annihilate back into nothingness. It's as if the vacuum is constantly creating and destroying pairs of particles, a quantum magic show that never stops performing. This isn't just theoretical speculation. The effects of vacuum fluctuations have been measured in the laboratory. There's something called the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force. This happens because the space between the plates can support fewer virtual particle fluctuations than the space outside, creating a kind of quantum pressure that pushes the plates together. The vacuum also contains what physicists call fields, invisible influences that fill all of space and give particles their properties. There's the electromagnetic field, which carries light and radio waves. There's the Higgs field, which gives particles mass. There are fields associated with the strong and weak nuclear forces. These fields exist everywhere, even in regions that appear completely empty, creating a kind of invisible landscape that fills the universe. But here's where things get really interesting when we think about cosmic boundaries. If space itself is filled with these fluctuating fields and virtual particles, then what we call empty space is actually a very specific kind of environment with particular properties. The vacuum has a definite energy density, a specific set of physical laws, and characteristic behavior patterns. This raises profound questions about what lies beyond the universe's observable boundary. Is the space beyond our cosmic horizon filled with the same kind of vacuum we observe locally? Do the same quantum fields extend out to infinite distances? Or might there be regions where the vacuum has different properties, where different fields dominate, where the very nature of empty space is altered? Some theories in physics suggest that there might be multiple vacuum states, different ways that empty space can organize itself. It's a bit like water, which can exist as ice, liquid, or vapor depending on temperature and pressure. The vacuum might exist in different phases, each with its own characteristic properties and particle interactions. If this is true, then the universe might contain vast regions where space itself behaves differently than it does in our cosmic neighborhood. There could be domains where particles have different masses, where forces have different strengths, where the basic rules of physics take on different forms. These would be separated by boundaries called domain walls, cosmic transition zones where one type of vacuum gives way to another. The idea of different vacuum states also relates to something called the multiverse, the hypothesis that our observable universe is just one of many universe-like regions in a much larger cosmic structure. In some versions of multiverse theory, each universe exists in its own vacuum state, with its own set of physical laws and constants. The boundaries between these universes would be the ultimate cosmic edges, transitions between different realms of existence. But even if the vacuum is the same everywhere, its properties still affect how we think about cosmic boundaries. The energy density of empty space, which is related to dark energy, influences the expansion rate of the universe, and thus the location of our cosmic horizon. The quantum fields that fill space determine what kinds of particles and forces can exist, shaping the kinds of structures and phenomena that are possible. There's also the possibility that the vacuum itself is not stable over very long time periods. Some theories suggest that the current state of empty space might be metastable, meaning it's stable for now, but could potentially transition to a lower energy state in the future. If this happened, it would create a bubble of new vacuum that would expand at the speed of light, fundamentally altering the properties of space wherever it passed. Such a vacuum decay event would represent the ultimate cosmic boundary, an expanding sphere beyond which the laws of physics as we know them would no longer apply. Fortunately, if such an event is possible, it appears to be extremely unlikely to happen any time in the foreseeable future. The universe has been stable for nearly 14 billion years, which suggests that our current vacuum state is quite robust. But perhaps the most remarkable thing about the quantum vacuum is that it reminds us that nothingness is actually somethingness in disguise. The space between galaxies, which appears empty to our senses, is actually filled with invisible activity, quantum fluctuations, and field oscillations that never cease. It's like discovering that silence is actually filled with music pitched too high or low for us to hear. This reframes our entire conception of cosmic emptiness. The vast spaces between galaxy clusters, the apparent voids in the cosmic web, are not actually empty, but filled with a subtle, invisible activity that shapes reality at the most fundamental level. Even if we could somehow travel to the most isolated region of the universe, billions of light years from the nearest star, we would still be surrounded by the quiet hum of quantum activity. And so the vacuum becomes another character in our cosmic story, not a passive stage but an active participant in the drama of existence. It's the invisible foundation on which all visible reality rests, the quantum soil in which particles and forces take root. Understanding its properties and extent becomes crucial for understanding what lies beyond our cosmic horizon and how the universe itself might be bounded or boundless. What if our entire universe is just one room in an infinite cosmic apartment building? It sounds like science fiction, but it's actually a serious possibility that emerges from our best theories about the nature of reality. The multiverse, as it's called, is the idea that what we think of as the universe might actually be just one of countless universes, like regions in a much vaster structure. There are several different ways that multiverses might arise, each based on different aspects of physics and cosmology. The simplest version comes from cosmic inflation, that period of exponential expansion in the very early universe. If inflation happened here, it probably happened elsewhere too, creating bubble universes scattered throughout a larger inflating space. Our observable universe would be just one such bubble, surrounded by countless others, each potentially with its own laws of physics and physical constants. Picture it like soap bubbles forming in a cosmic bath, each bubble representing a separate universe. The walls between bubbles would be regions of space still undergoing inflation, stretching so rapidly that no information could ever pass from one bubble to another. Each universe would be causally isolated from all the others, a completely separate realm of existence with its own history and destiny. But that's just one type of multiverse. Quantum mechanics suggests another possibility, that every quantum measurement creates a branching point where reality splits into multiple versions. When a particle's quantum state is measured, instead of randomly collapsing into one outcome, the universe splits into separate branches, each containing a different outcome. This creates an ever-branching tree of realities, with new universes being created constantly as quantum events occur throughout the cosmos. In this quantum multiverse, there would be versions of reality where every possible outcome of every quantum event actually happened somewhere. There would be universes where different stars formed, where life evolved differently, where you chose different cereals for breakfast this morning. It's like living in an infinite library, where every possible story is written and exists simultaneously on different shelves. Then there's the mathematical multiverse, perhaps the strangest idea of all, that every mathematically consistent structure actually exists as a physical reality. Our universe appears to be described by certain mathematical equations, the laws of physics as we know them. But there are infinitely many other possible mathematical structures, each potentially describing a different kind of universe, with different laws, different particles, different organizing principles. In this view, mathematics doesn't just describe reality, it is reality. Every possible universe that can be mathematically formulated actually exists somewhere in the vast space of all possibilities. Our universe is special to us not because it's unique, but simply because it's the one we happen to inhabit, the one whose laws allow observers like us to exist and wonder about cosmic boundaries. If any of these multiverse theories are correct, then the question, what's at the edge of the universe, becomes much more complicated. Our universe might have edges, but those edges would border other universes rather than emptiness. The cosmic boundaries we've been discussing, the limits of observation and interaction, might be boundaries between different realms of existence rather than absolute limits on reality itself. This reframes our entire perspective on cosmic isolation and connection. In a single universe model, the regions beyond our observable horizon are inaccessible, but presumably similar to what we can see. In a multiverse model, those regions might contain universes so different from ours that the very concepts of space, time, matter, and energy take on completely different meanings. Some multiverse theories suggest that the different universes might have different dimensionalities. While our universe has 3 dimensions of space and 1 of time, other universes might have more or fewer spatial dimensions, different numbers of time dimensions, or organizational principles we can't even imagine. The edges of our universe might border realms where geometry itself works differently. There's also the possibility of a hierarchical multiverse, where multiverses exist within larger multiverses in an endless nested structure. Our local group of bubble universes might be part of a larger structure, which is itself part of something even larger, extending upward in scale without limit. In such a scenario, the concept of an ultimate boundary becomes meaningless, as there would always be larger scales of organization beyond whatever level we might consider. But multiverses also raise deep questions about observation and knowledge. If other universes are causally isolated from ours, then by definition we can never observe them directly or receive information from them. They might influence our universe gravitationally if they're close enough, but we could never visit them or communicate with their inhabitants, if any exist. This creates an interesting philosophical puzzle. If we can never observe other universes, in what sense do they exist? Some scientists argue that the multiverse hypothesis is unscientific precisely because it makes predictions about unobservable realms. Others counter that many accepted theories in physics, from quantum mechanics to general relativity, make claims about unobservable aspects of reality. The multiverse also changes how we think about the specialness or typicality of our cosmic home. In a single universe, the fact that our region of space has conditions suitable for life might seem like an extraordinary coincidence. But in an infinite multiverse containing every possible variation, universes like ours would be not just possible but inevitable. We exist in a life-friendly universe, not because of cosmic design, but because only life-friendly universes can contain observers to notice their life-friendliness. There's something both humbling and liberating about the multiverse concept. Humbling because it suggests that our entire observable universe, vast as it is, might be just an infinitesimal fraction of total reality. Liberating because it suggests that the boundaries that seem to limit us, the cosmic horizons beyond which we cannot see or travel, are not absolute limits, but simply the edges of our local cosmic neighborhood. And yet, even in an infinite multiverse, the questions that drive our curiosity remain meaningful. Understanding the boundaries of our own universe, the limits of our own cosmic horizon, remains important for understanding our place in the scheme of things. Even if there are countless other universes beyond our reach, this universe is still our home, our context, our frame of reference for all experience and knowledge. In a way, the multiverse concept brings us back to one of the fundamental insights of our cosmic journey, that reality is far stranger and more wonderful than our everyday experience suggests. Whether the universe is singular or multiple, finite or infinite, bounded or boundaryless, it remains a source of endless wonder and gentle mystery, a cosmic home that's both intimate and infinite, familiar and forever strange. Infinity is a peculiar thing. It's not really a number, more like a concept having an existential crisis. It represents something without limit, without end, without boundary, and yet we use it casually in mathematics, as if it were as well behaved as the number 7. When we start thinking about the edge of the universe, infinity inevitably shows up to complicate matters, bringing with it questions that can make your head spin gently, like a cosmic merry-go-round that never stops. There are actually different kinds of infinity, which sounds like a contradiction, but makes perfect sense once you start thinking about it mathematically. The simplest kind is countable infinity, the infinity of counting numbers, 1, 2, 3, 4, and so on forever. No matter how high you count, there's always another number waiting. This infinity has a beginning. It starts with 1, but it has no end. Then there's the infinity of real numbers, which is somehow larger than the infinity of counting numbers. Between any two numbers, say 1 and 2, there are infinitely many other numbers, 1.1, 1.01, 1.001, and so on. This creates what mathematicians call uncountable infinity, an infinity so dense and rich that you can't even make a list of all its members. When cosmologists talk about infinite space, they're usually thinking about something like the infinity of real numbers, dense and continuous, extending without limit in all directions. But the question immediately arises, infinite in what sense? Is space infinite in extent, stretching forever in all directions? Or might it be finite but unbounded, like the surface of a sphere which has no edge but still has a definite area? This distinction is crucial for understanding cosmic boundaries. A finite but unbounded universe would be like living on the surface of a sphere, but in 3 dimensions instead of 2. You could travel in any direction for as long as you liked and never reach an edge, but you would eventually return to your starting point. The universe would have a definite volume, a specific amount of space, even though that space would have no boundary. On the other hand, an infinite universe would extend forever in all directions, containing infinite amounts of matter and energy, infinite numbers of galaxies and stars and planets. In such a universe, every possible arrangement of matter would not just be possible, but would actually occur infinitely many times. There would be infinitely many copies of our solar system, infinitely many versions of Earth, infinitely many versions of you reading these words. This leads to some deeply strange implications. In an infinite universe with finite possibilities for how matter can be arranged, every possible arrangement must repeat infinitely often. The laws of physics limit how particles can be combined and organized, creating a vast but finite number of possible configurations for any given region of space. If space is infinite but these configurations are finite, then repetition becomes inevitable. Imagine an infinite library containing every possible book. Since there are only so many ways to arrange letters on a page, and only so many pages you can fit in a book, the library would necessarily contain infinite copies of every possible book, including the one you're holding right now, along with infinite variations where single words or letters are different. But infinity creates puzzles as well as possibilities. If the universe is infinite, then it contains infinite amounts of matter and energy. This seems to conflict with conservation laws, which suggest that energy cannot be created or destroyed. How can infinite amounts of energy exist without having been created from nothing? One answer is that, in an infinite universe, conservation laws might apply locally, but not globally. Energy might be conserved within any finite region of space, but the total energy of an infinite universe might itself be infinite, or even undefined. It's like asking for the sum of all integers. Positive and negative numbers might balance locally, but the total sum is meaningless. There's also the question of how an infinite universe could have evolved from the Big Bang. If the universe is infinite now, it was probably infinite then too, which means the Big Bang involved infinite amounts of matter and energy appearing simultaneously at infinite locations. This isn't an explosion in the usual sense, but an infinite beginning that challenges our normal concepts of causation and physical processes. Some cosmological models avoid these infinities by proposing that the universe is finite but very large, perhaps much larger than the observable universe, but still having a definite size and total mass. In such models, the universe might be shaped like a hypersphere, curved in 4-dimensional space, in a way that makes it finite but unbounded. like a three-dimensional version of a sphere's surface. Other models suggest that the observable universe is just one patch in an infinite cosmic landscape, where conditions vary from place to place across vast distances. In some regions, the laws of physics might be different, the vacuum might have different properties, or space itself might have different geometrical characteristics. The infinity of such a cosmos would contain not just infinite repetitions of familiar structures, but infinite variations and possibilities we can barely imagine. But perhaps the most profound aspect of cosmic infinity is how it affects our understanding of uniqueness and significance. In a finite universe, rare events and improbable arrangements might truly be special. But in an infinite universe, every possible event happens infinitely often, making nothing truly unique and everything simultaneously common and rare. This creates a paradox of cosmic significance. On one hand, if everything that can happen does happen infinitely often, then nothing we do or experience is truly unique. On the other hand, the fact that we exist at all in an infinite sea of possibilities might be seen as infinitely improbable and therefore infinitely precious. Mathematics also suggests that there might be different levels of infinity in cosmic structure. If there are infinitely many universes, each containing infinitely many galaxies, each containing infinitely many stars, we get infinity nested within infinity, creating hierarchical structures of endless complexity. And yet, for all its mathematical precision, infinity remains something of a mystery. We can manipulate it with equations, we can reason about it logically, but we cannot directly experience or observe true infinity. Our finite minds grapple with the concept of the limitless, using finite mathematics to explore infinite possibilities. In the end, whether the universe is finite or infinite, bounded or boundaryless, might be less important than the fact that we can ask such questions at all. The mathematics of forever reminds us that reality might be far stranger and more wonderful than our everyday experience suggests, extending beyond our comprehension in ways that inspire both humility and wonder. And perhaps that's the most beautiful aspect of cosmic infinity. Not that it provides answers, but that it keeps the questions alive, stretching our imagination toward horizons that recede forever into the mathematical distance. The universe has been growing for nearly 14 billion years, and it's not planning to stop anytime soon. In fact, thanks to dark energy, the expansion is actually accelerating, which means that the cosmic boundaries we've been exploring are not fixed features but moving targets, constantly changing as space stretches and time unfolds. The edge of the universe, such as it is a dynamic, evolving boundary that will look very different in the distant future than it does today. Currently, our observable universe extends about 46 billion light-years in every direction, a sphere of visibility that grows slightly larger each day as light from more distant regions finally reaches us. But this growth is deceptively slow compared to what's happening at larger scales. The galaxies at the edge of our cosmic horizon are receding from us so rapidly that they're barely keeping pace with the expansion of our observable boundary. Some are already losing the race. Over the next few billion years, this process will accelerate. Galaxies that we can see clearly today will gradually fade from view as they're carried beyond our cosmic horizon by the expansion of space. Their light will become more and more redshifted, stretched to longer and longer wavelengths, until it fades below the threshold of detectability. One by one, the lights of distant galaxies will go out, not because the galaxies themselves are dying, but because their light can no longer reach us across the ever-expanding cosmic gulf. This creates a rather melancholic vision of the far future. Imagine astronomers billions of years from now, equipped with telescopes far more advanced than anything we have today. looking out at a much emptier universe. Most of the galaxies visible to us will have vanished from their view, receded beyond their cosmic horizon into permanent isolation. The universe will appear to be less connected, less populated, more lonely than the cosmos we observe today. But the expansion doesn't stop there. If dark energy continues to dominate and grow stronger over time, it could lead to even more dramatic changes in cosmic structure. There's a scenario called the Big Rip, where the expansion of space becomes so violent that it eventually tears apart galaxies, solar systems, planets, and ultimately even atoms themselves. In this rather extreme future, the boundaries of the observable universe would become increasingly irrelevant as the expansion overwhelms all other forces. First, galaxy clusters would be torn apart as the space between galaxies expands faster than their gravitational attraction can overcome. Then, individual galaxies would be shredded as dark energy overcomes the forces holding stars in orbit. Eventually, even the electromagnetic forces that hold atoms together would be overcome by the expansion, leading to a universe filled with isolated, fundamental particles racing away from each other at ever-increasing speeds. Fortunately, this Big Rip scenario, if it happens at all, is still many billions of years in the future. Current estimates suggest it wouldn't occur for at least 100 billion years, giving the universe plenty of time for other interesting developments. Stars will live and die, new stars will form, life might evolve in countless new forms, and perhaps intelligence will find ways to adapt to or even influence the cosmic expansion. But there are other possible futures as well. Dark energy might not be constant over time. It could weaken, allowing the expansion to slow down, or even reverse. Some models suggest that dark energy might oscillate, driving cycles of expansion and contraction over vast timescales. In such scenarios, the current period of accelerating expansion might be just one phase in an endless cosmic breathing cycle. If the expansion were to reverse, we'd enter a phase cosmologists call the Big Crunch, where space would contract, galaxies would move toward each other rather than away, and our cosmic horizon would actually grow larger as previously isolated regions came back into causal contact. The universe would become more connected rather than less connected over time. There's also the possibility that the expansion might reach a steady state, neither accelerating nor decelerating, but maintaining a constant rate. In this scenario, the cosmic horizon would stabilize at some maximum distance, creating permanent boundaries between different regions of space. Some parts of the universe would remain forever isolated from others, but the boundaries would be fixed rather than evolving. The far future also depends on what happens to matter and energy over cosmic timescales. Protons, the building blocks of atomic nuclei, might not be stable forever. Some theories suggest they could decay over incredibly long timescales, much longer than the current age of the universe, but finite nonetheless. If protons decay, then eventually all atomic matter would dissolve into lighter particles and radiation, fundamentally changing the nature of cosmic structure and the meaning of boundaries. Black holes, too, play a role in cosmic futures. Through Hawking radiation, they slowly evaporate over time, returning their mass energy to the universe as radiation. For stellar mass black holes, this process takes much longer than the current age of the universe, but for smaller black holes, it could happen much faster. In the very far future, black hole evaporation might be one of the last sources of energy in an otherwise cold, expanded universe. These deep time scenarios affect how we think about cosmic boundaries in profound ways. The edges and horizons that seem so fundamental to our current understanding might be temporary features, artifacts of the particular era in cosmic history that we happen to inhabit. The boundaries that limit our observation and interaction today might dissolve, transform, or give way to entirely different kinds of limits in the cosmic futures that await. But perhaps the most remarkable thing about the expanding edges of tomorrow is that they remind us that the universe is not a static stage, but a dynamic, evolving story. The boundaries we observe today are chapters in an ongoing narrative that began nearly 14 billion years ago and will continue for billions or trillions of years to come. We exist in the middle chapters of this cosmic story, able to observe the consequences of the past and speculate about the possibilities of the future. And in this vast cosmic story, the question of edges and boundaries remains eternally relevant. Whether the universe expands forever, contracts back on itself, or reaches some kind of equilibrium, the limits of observation and interaction will continue to shape how intelligence, wherever it arises, understands its place in the cosmic scheme. The expanding edges of tomorrow are not just physical boundaries, but epistemological ones, limits on what can be known and experienced by any observer, anywhere in space and time. In a way, this ongoing evolution of cosmic boundaries is both humbling and inspiring. Humbling because it reminds us that our current view of the universe is just one snapshot in an ongoing cosmic movie. Inspiring because it suggests that the story of cosmic exploration and understanding is far from over, that future observers will face new questions and discover new mysteries as the boundaries of reality continue to shift and evolve around them. Some questions, it seems, are designed to stay mysterious. No matter how clever our theories become, how sensitive our instruments grow, or how far we extend our reach into the cosmos, there will always be aspects of reality that remain forever beyond our grasp. This isn't a failure of science or human curiosity. It's a fundamental feature of existence itself, woven into the very structure of space and time. The most obvious limitation comes from the speed of light and the expansion of space. There are regions of the universe from which light will never reach us, not because our telescopes aren't good enough, but because the expansion of space carries those regions away faster than their light can catch up to us. These areas exist beyond what's called our particle horizon, the boundary that marks the farthest distance from which we can ever receive information. But it gets more subtle than that. Even for regions within our particle horizon, there are things we can never know with certainty. We can see how galaxies looked in the distant past when their light began its journey toward us, but we cannot know how they look right now. The present moment of distant objects is hidden from us by the travel time of light, creating a kind of temporal blindness that no technology can overcome. There's also something called the event horizon, which marks the boundary beyond which light emitted today will never reach us in the future. Due to the accelerating expansion of the universe, this event horizon is actually closer than our particle horizon, sitting at about 16 billion light-years away. This means there are galaxies we can observe today, whose futures we will never witness. We can watch their ancient past, but their present and future will gradually fade from view as their light becomes too redshifted to detect. These observational limits create permanent gaps in our cosmic knowledge. We can never conduct a complete census of the universe, never map all the galaxies, never account for all the matter and energy in existence. There will always be regions of space that remain fundamentally unknowable, not just practically inaccessible, but theoretically unobservable. Quantum mechanics adds another layer of fundamental mystery. The uncertainty principle tells us that there are aspects of reality that cannot be measured simultaneously with perfect precision. Position and momentum, energy and time. These pairs of properties are linked by fundamental uncertainties that no amount of technological improvement can eliminate. The universe preserves certain secrets at the quantum level, maintaining areas of irreducible mystery in the heart of physical law. Even more profound is the question of what lies beyond the Big Bang. Our cosmic timeline has a beginning, but what came before that beginning? The question might be meaningless if time itself started with the Big Bang, but it might also point to deeper levels of reality that are permanently inaccessible to observation. We cannot receive information from before the universe became transparent, cannot probe the conditions that gave rise to the Big Bang itself. The nature of dark matter and dark energy represents another category of possibly permanent ignorance. We can observe their effects, measure their influence on cosmic structure and expansion, but we cannot directly detect or interact with these mysterious components of reality. They might forever remain shadows cast by invisible actors, their true nature hidden behind veils of cosmic inscrutability. If the multiverse exists, it creates the ultimate boundary of unknowability. By definition, other universes are causally isolated from ours, meaning we can never observe them directly or receive information from them. They might influence our universe gravitationally if they're close enough, but we could never visit them, communicate with their inhabitants, or verify their existence through direct observation. The multiverse hypothesis makes claims about vast realms of reality that are fundamentally unverifiable. But perhaps the deepest unknowability comes from the problem of self-reference. We are part of the universe we're trying to understand, observers embedded within the system we're attempting to observe. This creates unavoidable blind spots and biases in our cosmic perspective. We can never step outside the universe to view it objectively, never escape our position as inside observers trying to understand the totality from within. There's also the question of whether some aspects of reality might be genuinely random, fundamentally unpredictable, even in principle. Quantum mechanics suggests that certain events, like the decay of radioactive nuclei, are truly random, rather than just appearing random due to hidden factors we haven't discovered. If the universe contains genuine randomness, then there are aspects of the future that are unknowable, not just to us, but to the universe itself. The mathematics of infinity creates its own category of unknowability. If the universe is truly infinite in extent, then it contains infinite amounts of information, infinite numbers of possible events and structures. No finite intelligence, no matter how advanced, could ever catalogue or understand the totality of an infinite universe. There would always be more to discover, always new regions to explore, always deeper levels of complexity to unravel. And then there are the philosophical limits of knowledge itself. Even if we could somehow observe every particle in the universe, predict every quantum event, map every galaxy beyond our current horizon, would we truly understand what it all means? The deepest questions about existence, consciousness, purpose, and meaning might lie beyond the reach of scientific investigation, preserved in realms of mystery that no amount of data can illuminate. But here's something wonderful about these limitations. They're not obstacles to overcome, but features to appreciate. The existence of unknowable realms means that mystery is not a temporary condition to be cured by advancing knowledge, but a permanent aspect of existence that keeps wonder alive. No matter how much we learn, there will always be more questions to ask, more mysteries to contemplate, more horizons to wonder about. In a universe where everything could be known, where every question could be answered, where every mystery could be solved, existence might become rather boring. The permanent presence of unknowability ensures that reality remains forever interesting, forever capable of inspiring awe and curiosity. It guarantees that the conversation between intelligence and cosmos can never be concluded, only continued. There's something profoundly comforting about living in a universe with built-in mysteries. It means that no matter how advanced human knowledge becomes, no matter how sophisticated our theories or powerful our instruments, there will always be room for wonder, always space for the gentle acknowledgement that we are small, finite beings, contemplating something vast and fundamentally mysterious. And perhaps that's the most beautiful boundary of all. Not a wall that blocks our progress, but a horizon that keeps receding, always offering new questions to replace the ones we've answered, always preserving the sense that reality is deeper and stranger and more wonderful than we can ever fully comprehend. If you could somehow step outside the universe and look at it from the outside, what would you see? It's a thought experiment that immediately runs into a logical problem. There is no outside the universe to step into. The universe, by definition, is everything that exists, all of space and time and matter and energy. Asking what's outside, it is a bit like asking what's north of the North Pole, a question that seems meaningful until you realize it's based on assumptions that don't actually apply. But let's play with this impossible scenario anyway, because sometimes the most interesting insights come from impossible thought experiments. Imagine you're a cosmic observer with the ability to perceive the universe from some theoretical external vantage point. What kind of view would greet you? If the universe is finite and bounded, you might see it as some kind of cosmic bubble, a three-dimensional sphere floating in, well, in what? The question immediately recurses because whatever the universe is floating in would presumably be part of a larger reality, and then we'd have to ask what that larger reality is floating in, and so on forever. It's like asking what container holds all the containers, including itself. If the universe is infinite in extent, then your external view would face a different kind of problem. How do you observe something infinite from outside when there is no outside? An infinite universe has no boundary to stand beyond, no edge to peer over. It extends forever in all directions, making the very concept of an external viewpoint meaningless. But perhaps we're thinking about this wrong. Maybe the outside we're trying to imagine isn't spatial but dimensional. Our universe appears to have 3 dimensions of space and 1 of time, but theoretical physics suggests that reality might have additional dimensions that we can't perceive directly. String theory, for instance, proposes that space might have 10 or 11 dimensions, with the extra dimensions somehow compactified or hidden from our normal experience. From this higher dimensional perspective, our 3-dimensional universe might appear as a kind of membrane or surface embedded in a larger dimensional space. It would be like how a 2-dimensional ant crawling on the surface of a balloon might not realize that its entire world is embedded in 3-dimensional space. From our hypothetical higher dimensional viewpoint, the universe might have boundaries and shapes that are completely invisible to us 3-dimensional inhabitants. This raises fascinating questions about what such boundaries might look like. If our universe is a 3-dimensional surface in 4-dimensional space, then its edge would be a 2-dimensional boundary, perhaps analogous to the surface of a soap bubble. But what would lie beyond this boundary? More universe-like regions? Empty, higher dimensional space? Other membrane universes floating nearby like cosmic jellyfish in some vast dimensional ocean? The view from nowhere also forces us to confront the relationship between space and the things that occupy it. When we think about the edge of the universe, we're usually thinking about the edge of the matter and energy within it. But space itself might extend beyond the matter, creating empty regions that are still part of the universe, even though they contain nothing observable. It's like the difference between a city and the land it's built on. The city has boundaries where the buildings end and the countryside begins, but the land itself might extend much further. Similarly, the observable matter in our universe might have boundaries, while the space containing it continues indefinitely in all directions. From our impossible external viewpoint, we might see the universe as an island of activity in an ocean of empty space, or as a growing bubble of space-time expanding into some larger dimensional framework. We might observe multiple universes scattered throughout this framework, like cosmic archipelagos, each with its own history and physical laws. But the view from nowhere also reveals something profound about the nature of perspective itself. Every view is a view from somewhere, shaped by the position and nature of the observer. Even our hypothetical external observer would have their own limitations, their own blind spots, their own conceptual frameworks that shape what they can perceive and understand. In a way, this brings us back to the insight that all observation is local. All knowledge is situated. There is no view from nowhere in the literal sense. No perspective that encompasses everything without being shaped by the specific circumstances of the observer. Even an omniscient external observer would see the universe from their own unique vantage point, with their own particular way of organizing and interpreting information. This has profound implications for how we think about cosmic boundaries. The edges and limits we perceive might be as much about our nature as observers as they are about the actual structure of reality. Our cosmic horizons are defined by our position in space and time, our dependence on light for information, our embedding within the very system we're trying to understand. A different kind of observer, perhaps one not bound by the speed of light, or not embedded within space-time in the same way we are, might perceive very different boundaries, or perhaps no boundaries at all. The universe's edges might be observer relative, different for different kinds of intelligence with different sensory capabilities and conceptual frameworks. And yet, there's something beautiful about our limited, embedded perspective. We don't have a view from nowhere, but we have a view from here, from this specific location in space and time, this particular evolutionary history, this unique vantage point that no other observer in the universe can exactly replicate. Our cosmic boundaries, our observational horizons, our fundamental limitations, these aren't failures of perspective but features of it. They remind us that we are not detached observers studying the universe from outside, but participants embedded within it, shaped by it, arising from its very substance and processes. In the end, the view from nowhere teaches us something important about the view from somewhere. We cannot step outside the universe to see it objectively, cannot escape our position as inside observers, with finite capabilities and embedded perspectives. But this limitation is also what makes our cosmic exploration meaningful, what gives weight and poignancy to our questions about boundaries and edges. We are the universe becoming conscious of itself, matter and energy organized in ways that allow for self-awareness and curiosity. We cannot see ourselves from outside, but we can wonder about what such a view might reveal. And in that wondering, in that gentle reaching toward impossible perspectives, we discover something profound about the nature of consciousness, curiosity, and our strange position as embedded observers, contemplating the cosmic whole that contains us. Perhaps the most beautiful thing about the universe's edge is that it teaches us something important about wonder itself. After wandering through cosmic horizons and quantum uncertainties, through expanding space and invisible matter, through multiverses and mathematics, we arrive at a curious conclusion. The universe's boundaries, such as they are not walls that confine us, but invitations to embrace something larger than comprehension. Throughout human history, boundaries have often been sources of frustration or fear. We've seen them as obstacles to overcome, barriers to break through, limits that constrain our freedom and possibility. But cosmic boundaries are different. They're not imposed from outside, but emerge from the very structure of existence itself. They're not arbitrary restrictions, but fundamental features of reality, woven into the fabric of space and time and observation. The horizon of the observable universe doesn't exist because someone built a cosmic wall to keep us from seeing farther. It exists because light has a finite speed, and the universe has a finite age. It's a boundary created by information and time, by the fact that knowledge takes time to travel, and that time itself had a beginning. In a strange way, this boundary is what makes the universe knowable at all, what creates the possibility of coherent observation and understanding. Without cosmic boundaries, the universe might be an overwhelming chaos of infinite information arriving simultaneously from infinite distances. The limits that seem to constrain us actually create the conditions within which awareness and curiosity can exist. They carve out a space of manageable mystery, a cosmic neighborhood small enough to explore, but large enough to inspire wonder. There's also something profound about living in an era when these boundaries are still mysterious. We exist at a unique moment in cosmic history, when the universe is old enough to have developed complex structures and life, but young enough that many fundamental questions remain open. We can see the cosmic microwave background, that afterglow of the Big Bang, but we cannot see beyond it. We can observe galaxies receding to our cosmic horizon, but we cannot know what lies beyond. Future civilizations, if they arise, might inhabit a universe where many of these questions have been answered, or where the boundaries have shifted in ways that reveal new mysteries while obscuring others. The expanding universe might carry most galaxies beyond their observational reach, making their cosmos appear emptier and more isolated than ours. Or new physics might be discovered that transforms our understanding of boundaries and edges in ways we cannot currently imagine. But perhaps the most remarkable thing about cosmic boundaries is how they mirror the boundaries of human experience more generally. We all live within horizons of various kinds, the limits of our lifespan, the boundaries of our knowledge, the horizons of our empathy and understanding. We cannot see beyond our own death, cannot know everything there is to know, cannot fully understand experiences radically different from our own. These personal boundaries, like cosmic ones, might seem limiting at first, but they're also what gives shape and meaning to human existence. A life without boundaries would be a life without form, without narrative structure, without the poignancy that comes from knowing our time and knowledge and perspective are finite. The edges of our experience create the frame within which meaning can emerge. In embracing cosmic boundlessness, we learn something about embracing the bounded nature of our own existence. We don't need to understand everything to find wonder in what we can understand. We don't need to live forever to find meaning in the time we have. We don't need to transcend all limitations to discover beauty and purpose within the limitations that define us. The universe's boundaries also teach us about the relationship between knowledge and mystery. As our observations have extended farther into space and deeper into time, we might have expected mystery to diminish, questions to be resolved, boundaries to be eliminated. But the opposite has happened. Each new discovery has revealed new questions. Each expanded horizon has shown us new boundaries beyond. This suggests that mystery is not a temporary condition to be cured by advancing knowledge, but a structural feature of the relationship between consciousness and cosmos. The universe seems designed to always offer more questions than answers, more horizons than destinations, more wonder than comprehension. This isn't a failure of science or human understanding. It's a gift that keeps the conversation between mind and reality forever fresh and engaging. And there's something deeply comforting about existing in a universe with built-in mysteries. It means that no matter how much we learn, no matter how far we extend our reach or refine our theories, there will always be room for wonder, always space for the quiet acknowledgement that reality is deeper and stranger than we can fully grasp. The boundless universe doesn't diminish human significance, it amplifies it. We are the part of the universe that has become conscious, curious, capable of asking questions about cosmic boundaries and finding meaning in the asking itself. We are matter and energy organized in ways that allow for self-reflection and wonder, temporary eddies of complexity in the cosmic flow that can contemplate the whole of which we are part. In embracing the boundless, we discover that boundaries themselves can be sources of beauty rather than frustration. The limits of our cosmic vision create the frame within which we can perceive and appreciate what lies within our reach. The horizons that mark the edges of our knowledge create the context within which discovery becomes meaningful. The mysteries that persist beyond our understanding create the space within which wonder can flourish. Perhaps this is the deepest lesson of our journey to the edge of the universe, that the search for boundaries reveals not walls, but horizons, not endings, but beginnings, not limitations, but invitations to embrace mystery as a fundamental feature of existence. The universe doesn't need edges to be complete, and neither do we. We are already whole, already sufficient, already meaningful within whatever boundaries define our experience. The edge of the universe, such as it is not somewhere out there in the distant cosmos, but here in the interface between consciousness and mystery, in the gentle recognition that we are both bounded and boundless, finite and infinite, temporary arrangements of matter, contemplating the eternal questions that give existence its wonder and meaning. In a world full of easy answers, the universe offers us something precious, questions that stay questions. After our gentle journey through cosmic horizons and quantum mysteries, through expanding space and invisible matter, we might expect to arrive at some grand conclusion, some final answer to where the universe ends or how reality is bounded. But instead, we find ourselves in a place of comfortable unknowing, surrounded by mysteries that resist simple resolution. There's something remarkably soothing about this state of cosmic uncertainty. In our daily lives, not knowing often feels uncomfortable. We want to know if it will rain tomorrow, whether our plans will work out, what other people think of us. Uncertainty can create anxiety, doubt, restless searching for answers that might not exist or might not matter as much as we think they do. But cosmic not knowing is different. It's vast, patient, unhurried. It doesn't demand immediate resolution or practical application. It simply exists, like a gentle presence that surrounds us with infinite questions and infinite patience for the fact that we cannot answer them. The universe keeps its secrets not out of malice or indifference, but as a kind of gift, a way of ensuring that wonder remains alive in the cosmic conversation. Consider how different our relationship with reality would be if all questions could be answered, all mysteries solved, all boundaries mapped with perfect precision. We would inhabit a universe of completed knowledge, where every phenomenon could be predicted and explained, where nothing remained to inspire curiosity or awe. It would be like reading a book where all the surprises had been spoiled, where every plot twist was telegraphed in advance. Instead, we live in a universe that preserves mystery as a fundamental feature, not a temporary condition. The boundaries we've explored, the cosmic horizons that limit our observation, the quantum uncertainties that resist perfect measurement. These aren't flaws in the design of reality, but essential characteristics that keep existence interesting, beautiful, and alive with possibility. The comfort of not knowing extends beyond cosmology into the most intimate aspects of human experience. We don't know what dreams mean, why music moves us, how consciousness arises from matter, or what happens when we die. These unknowns might seem troubling at first, but they're also what gives depth and meaning to existence. Life without mystery would be life without poetry, without the gentle space for imagination and wonder. Our cosmic boundaries mirror these personal mysteries in beautiful ways. Just as we cannot step outside ourselves to observe our own consciousness objectively, we cannot step outside the universe to see its boundaries clearly. Just as the deepest questions about human existence resist easy answers, The deepest questions about cosmic structure remain wonderfully, persistently open, and there's something profoundly democratic about cosmic mystery. It doesn't matter how educated you are, how sophisticated your instruments, how advanced your theories. When it comes to the deepest questions about existence, we're all beginners, all equally positioned at the edge of the known, peering into the vast darkness of cosmic uncertainty with equal measures of curiosity and humility. The mysteries we've explored don't disappear with scientific progress. They deepen and multiply. Each new discovery reveals new questions. Each extended boundary shows us new horizons beyond. The observable universe grows larger over time, but so does our awareness of what lies beyond observation. Knowledge and mystery expand together, keeping pace like old friends walking side by side into an endless landscape. This suggests something beautiful about the nature of intelligence and curiosity. We're not designed to solve the universe like a puzzle and then move on to something else. We're designed for the ongoing conversation with mystery, for the endless dance between question and answer, discovery and wonder. Our minds are built for exploration rather than completion, for journey rather than arrival. The comfort of not knowing also offers a different relationship with time and mortality. If we could answer all questions and solve all mysteries, we might feel pressured to hurry, to accumulate knowledge as quickly as possible before our time runs out. But in a universe of persistent mystery, there's permission to slow down, to savor the questions themselves, to find meaning in the wondering rather than rushing toward answers that might not exist. There's also something beautifully humble about acknowledging the limits of human knowledge. We are remarkable creatures, capable of contemplating the universe's origin and fate, of mapping cosmic structure across billions of light years, of detecting the subtle signatures of invisible matter and energy. But we're also small, temporary, limited beings, embedded within the very system we're trying to understand. This combination of capability and limitation creates a poignant beauty in the human cosmic perspective. We can ask questions that span the universe, but we must ask them from our tiny planetary perch in one galaxy among trillions. We can theorize about multiverses and extra dimensions, but we remain bound by the speed of light and the expansion of space. We can contemplate infinity, but we must do so with finite minds and finite lifespans. And perhaps this is exactly as it should be. The universe doesn't need us to understand it completely to appreciate our place within it. We don't need to solve all mysteries to find meaning in the questions themselves. We don't need to transcend all boundaries to discover beauty and purpose within the limits that define our existence. The edge of the universe, wherever and whatever it might be, remains a gentle mystery that invites rather than intimidates. It reminds us that reality is larger than our comprehension, stranger than our theories, more wonderful than our wildest imagination. It offers not answers but better questions, not destinations but ongoing journeys, not completion but the endless possibility of continued discovery. In the end, the greatest comfort of not knowing might be that it keeps us human. In a cosmos of complete knowledge, we might lose our sense of wonder, our humility, our appreciation for the mysterious beauty that surrounds us. The universe's persistent mysteries ensure that we remain forever students rather than graduates, forever beginners in the vast school of existence, forever capable of being surprised and delighted by the strange, beautiful, utterly mysterious reality we call home. And so, we drift back from the edge of everything to the small, comfortable corner where you rest tonight. We've traveled to cosmic horizons and danced with infinity, wandered through expanding space and time stretched thin. We've discovered that the universe's edge might not be an edge at all, but something far stranger and more wonderful. In the end, perhaps that's the most beautiful discovery of all. The universe doesn't offer us neat boundaries or tidy answers. Instead, it gives us something far more precious: the gentle reminder that mystery and wonder are woven into the very fabric of existence. Every question we answer seems to bloom into three new ones, like cosmic flowers opening in the darkness. Tonight, as you settle into sleep, you're resting in a small pocket of warmth and safety, suspended in an ocean of space so vast that its edges, if they exist at all, lie beyond the reach of light itself. And yet, here you are, breathing quietly, thinking gently, part of the same cosmic story that began nearly 14 billion years ago and continues to unfold in ways we're only beginning to imagine. Sweet dreams from all of us here at Sleep Science. May your rest be as peaceful as the space between stars and as infinite as the questions that make us human.